So if we have gone over the mechanisms for SN1 and SN2 reactions, I'm sure we would have gone over the SN2 reaction, but if we have not, just in case we have not covered SN1 reaction mechanism in the lectures, I just want to go over that with you real quick. Now, the reaction name SN1, or I should say that's a mechanism name. SN1 is the name for the mechanism, and since you know what SN2 stands for, you might be able to guess what this stands for. This is unimolecular nucleophilic substitution reaction. Now, let's think about the mechanism for this. Just like the name suggests, this reaction, its rate determining step, or the hardest step, only involves unimolecule, because it's a unimolecular reaction, or just one molecule, and that's going to be the substrate. So at the rate determining step, there's only this one molecule that's involved, and what needs to happen for that is that the leaving group has to be eventually substituted by the solvent. This reaction is also called a solvolysis reaction, because the leaving group, its leaving and displacement is sort of guided by the solvation process or by the solvent, and so usually the solvent is what displaces the leaving group. But anyway, going back to the idea that it's a unimolecular rate determining step, what needs to happen is the leaving group actually has to leave. And so in the mechanism, the first step that's going to happen is the leaving group leaving. This is also the rate determining step. It's a fairly slow process compared to other steps. And the end result is going to be you get a carbocation and the leaving group that left. Okay. Now that we have a carbocation, normally tertiary bromide or tertiary halide, this is way too hindered, sterically hindered for any nucleophile to attack at this carbon. And so for this reason, for example, this substrate would never undergo an SN2 reaction, because the nucleophile could never directly attack at this very crowded tetrahedral sp3 carbon. But now that we have an sp2 hybridized, in other words, it's a trigonal planar flat species, and it's very reactive because it's a carbocation, which is unstable, as you remember. I guess I don't need the safety glasses anymore for now. And what we're going to do, the next thing that happens is the solvent will react with that. So we have the solvent molecule. Now, you may know from our discussion about SN2 reactions that something like an alcohol is moderate to poor-ish nucleophile. It can be a nucleophile because it has lone pairs of electrons, and it's somewhat loose basic. But unlike something like an alkoxide with an O negative charge, this is a lot weaker of a nucleophile. But because we have such a strong electrophile in the form of a carbocation, this is able to attack that. And so now we have this intermediate. And hopefully now you can see where we're going with this mechanism. That's our product. To get there, all we have to do is to use something as a base to pull off that extra proton. And that's our mechanism. In the last step here, what we did was use ethanol, or the solvent alcohol, as a base to pull off the extra proton. And once that proton is off, that oxygen has two pairs of lone pair electrons. It's neutral. That's our neutral product. So now that we've gone over the mechanism for SN1 reaction, I just want to point out a few things. Because in an SN1 reaction, we have the very unstable carbocation intermediate, there's some limitations on what the substrate can be. This is an ideal substrate for SN1 reaction because in the mechanism it produces a tertiary cation, which as far as carbocations go, that's one of the more ideal forms of carbocation, as you recall, because the very electrophilic electron deficient carbon, remember this carbon is not even meeting the octet. This cation is stabilized by three alkyl groups, in this case three methyl groups that are electron rich, or they're electron donating groups that can stabilize that extremely electron deficient carbon. And so for that reason, it's only something like a tertiary or sometimes maybe even a secondary cation, a secondary halide could undergo SN1 reaction, but really for SN1 it has to be either tertiary or secondary halide, or some sort of a leaving group. It has to be a tertiary or secondary substrate, or this reaction does not work. Now, either in the lab or in the lecture, you might actually see that there are sometimes primary example of SN1 reaction, and for those cases, that is sort of the exception to the rule. But think about the mechanism and why such exceptions can exist, because normally primary cation is so unstable that this really cannot exist. But in certain circumstance, maybe the primary cation is actually stabilized by resonance or something like that, and in those cases, even an SN1 solvolysis reaction could work with a primary substrate. In this experiment, you will want to figure out what kind of factors would favor SN1 reaction and what kind of factors or reaction conditions in a particular reaction favor SN2 reaction. And for that reason, you will want to spend some time taking a look at page 42 in your lab manual. I think there's a typo, it says just XXX number of factors, but it's meant to say at least four factors that you will want to consider in organizing your data. For example, if you're comparing chlorocyclohexane and bromocyclohexane as an example, comparing these two will reveal to you something about the choice of the leaving group, whether chloride as the leaving group would favor SN1 over SN2, or bromide as the leaving group would favor SN1 over SN2, or just more in general, having these two different leaving groups for both SN1 and SN2 reaction, is it going to make the reaction go faster, or is bromide going to make the either SN1 or SN2 go faster? And you may, so again, before you come into the lab though, you will want to create a table that looks something like this, where you have thought about different factors that you will want to study to come to a good conclusion about what sort of factors favor one reaction over the other at the end of your lab notebook, or possibly your lab report. This is a really insightful and an important experiment, so it may be really helpful for you to learn the lecture material if you actually do the detailed lab report on this experiment as opposed to the other ones. But anyway, you will want to spend some time thinking about organizing a table and actually making a table before you come to the lab, so that to consider the leaving group factor, you're going to compare these two as an example. By the way, this may or may not be the best pair to consider for the leaving group factor. It may be or may not be. I want you to I'll let you think about that. And when you're thinking about the list of chemicals, you will not want to think about them just from the names. You will want to draw the actual structures. Make sure that you actually have done that. That's actually part of the pre-lab assignment. You will want to use different reagents for SN1 and SN2 reactions. I'm just in this video I'm going to demonstrate an SN2 reaction only, but based on that you should be able to figure out how to perform the SN1 reaction as well. For the SN2 visual indicator we're using sodium iodide. And the reason is because sodium iodide is soluble in an organic solvent like acetone, but and that has to do with how it's very polarizable and whatnot. But sodium chloride and sodium bromide, on the other hand, those two salts do not stay dissolved in an organic solvent, and therefore they will precipitate out as soon as they're formed. And if the chloride or bromide gets kicked off as a leaving group, as in the case of an SN2 reaction, I guess that applies to SN1 as well, but in SN2, if these compounds do undergo SN2 reaction, they will kick off the corresponding halide, and that will form an insoluble salt with the sodium ion in an organic solvent, and they will precipitate out, and that's going to be your visual cue that the reaction either is happening or has completed. So here I have an empty test tube, and I'm going to take some, in this example I'm actually going to use benzyl chloride, not cyclohexane derivative, but I'm going to take a few drops from the chemical bottle, and I'm going to put 1, 2, 3 drops. Now I actually have some excess here, and that needs to go into a waste container, not into the and here I have a waste container just for this purpose, the excess. Remember the rule that no chemical should ever be poured back or pipetted back into the bottle that they came from. Yes, it does cost some money to get rid of waste, chemical waste, but that cost, it does not even remotely compare to the amount of cost that would be incurred if any of the reagent bottles were to be contaminated, and we just cannot take that risk, especially some of these bottles also are used for research purposes, and if anything is contaminated and we keep using that, sometimes we can spend 1 or 2 years doing a research project that doesn't work because of a contaminated reagent bottle. We just cannot take that risk, and for that reason, please remember this important rule. You do not ever pour anything back or pipette anything back into the reagent bottle. It's also a safety concern, because if you were to pipette back something that's cross-contaminated, say with moisture, back into a reagent bottle that's very reactive with reagent bottle that contains something that's very reactive with moisture, that could actually be very hazardous. So here I have the test tube with 3 drops of benzyl chloride that I got from a secondary container of benzyl chloride. Please don't use the primary reagent bottle that came from the chemical company, again, to not risk any cross-contamination for future. And what I'm going to do is add about 1 milliliter, that I'm going to measure with my calibrated pasteur pipette, and it's calibrated so that I know exactly where 1 milliliter should be on my pasteur pipette. I don't know if you can see, there's a marking on the pasteur pipette that marks where the 1 milliliter mark should be. And so I'm going to take about 1 milliliter of the sodium iodide solution in acetone, and add this to my test tube. And as I agitate this, I don't know if you can see very well in the video, but the moment I added it, there was no cloudiness, but as the time goes by, there's more cloudiness in the test tube. And let's think about where that cloudiness is actually coming from, and that must be coming from, again, insoluble salt that's precipitating. And remember, sodium iodide is soluble in this acetone solution, and of course so is benzyl chloride, which is an organic substance. It's soluble in acetone, the organic solvent. So the only thing that can be insoluble here is sodium chloride. That is precipitating out, and this is now evidence that the reaction took place. Now, in this demonstration reaction, I did not time how long the reaction took. It was almost, for the most part, instantaneous. The reaction happened enough that there was a visible amount of sodium chloride precipitating out, I'd say in the first 5-10 seconds. In your experiment, you will want to time this as well. We do have some stopwatches, but most of you may just want to use your phone like stopwatch app to just time how long it takes for the initial very clear sign of cloudiness appearing in the solution. Now, you don't necessarily have to wait till it's this cloudy. As soon as you can visually tell that there's definitely cloudiness that was newly formed, and that's when you want to stop your stopwatch and record the time. For a lot of some of these reactions, the reaction may be almost instantaneous, and you may not be able to record exactly how long it took, exactly how many seconds it took, or maybe even milliseconds, and that's fine. You just want to record that it was very fast or almost instantaneous. What we are interested in is that some of the reactions, it may take more than just a few seconds or maybe even minutes. And some reactions, you may even have to put this in a 50 degrees water bath to make it go. And that's what we're interested in. Okay. Now, even though in this demo I'm just doing one reaction, you will want to just for the time's sake, you will want to do 3, 4, or maybe even 5 or 6 reactions at a time. You just have to make sure that you label each test tube clearly to indicate exactly what is in it. And then go ahead and take 3 drops of, for the case of SN2 reaction, 3 drops of the organic substrate into each test tube, and then take up 1 milliliter, pipette in 1 milliliter of acetone into each test tube, and then once again have a table of data ready to go. That way you can just write down exactly how many seconds it took, like 10 seconds, 20 seconds, or what have you, into the data table directly, immediately as the reactions are happening. And again, some of the reactions will happen instantaneously, so having an organized table at the beginning before you start the reaction will really help, because as things are happening, you can write down your observations and how long each reaction is taking. After the reactions are done, let's say you finish all your SN2 reactions or all your SN1 reactions, whichever the ones you do first, you will want to clean the test tubes you will want to dump this in the designated waste container that your instructor, I'm sure, will let you know about. And after that, you will want to rinse these with DI water. Well, first you can rinse these with tap water, and then DI water, and then a little bit of acetone. And make sure that these test tubes are cleaned thoroughly. And the reason is we don't necessarily want to use 24 disposable glass test tubes for each student. We just want to limit that to 12. So you will have 12 test tubes for the first round, whether it's SN2 or SN1, and then you're going to have another round of 12 test tubes for the other reaction. Now, feel free to start from SN1 or SN2 reactions. It really doesn't matter, as long as you don't mix up the solvents or reagent solutions. For tips for organizing your test tubes, you might be able to just use your small Erlenmeyer flasks like these, and just line up maybe a few test tubes for reactions at a time, and have your substrates in there already, and then dispense in either sodium iodide solution or silver nitrate solution, depending on which part of the experiment you're doing.